For an entire century, scientists assured us of one certainty. Nothing could possibly illuminate the cosmic dark ages, that silent, starless epoch following the Big Bang when the universe lay dormant in absolute darkness. Yet the James Webb Space Telescope has shattered that conviction by peering beyond what the Big Bang's timeline should allow. Webb has discovered colossal blazing galaxies and enigmatic beacons of light in regions where only void should exist. Some emerged less than 300 million years after time itself began, and 9 others appeared even earlier, closer to the moment of creation than our theories permit. If these observations prove accurate, everything we believe about the universe's origins suddenly hangs in the balance, pointing toward cosmic forces that no one anticipated. What exactly has Webb witnessed? And why does it threaten to rewrite the universe's fundamental rules? The universe emerged as an inferno of incomprehensible heat and crushing pressure. But once the initial flash subsided, a profound silence descended across the cosmos. Hydrogen and helium, forged in the Big Bang's crucible, drifted as an enormous invisible fog. No stars existed, no galaxies formed, not even a solitary spark to pierce the quiet. Only an ocean of neutral gas. Cooling gradually as space expanded, temperatures plummeted to mere dozens of Kelvin, barely above absolute zero. In every direction, darkness reigned thick and complete, with nothing present to catch or scatter a single photon. Space itself stretched wider and colder, pulling atoms farther apart until even the faint afterglow of creation diminished to barely a whisper. Gravity operated in silence, gathering the first wisps of matter into increasingly dense clumps. But this process demanded millions of years. For eons, the universe remained a black ocean, each hydrogen atom floating in isolation, untouched by light. In this endless night, time appeared frozen. The only movement was gravity's slow, patient pull, methodically shaping the raw ingredients of everything yet to come. This was the cosmic dark age, an era when the universe waited, frozen and silent, for the first light to break its spell. Simulations of the early universe had long forecast a slow, methodical progression toward first light. According to these models, gravity initiated work by gathering dark matter into invisible halos, dense concentrations that would serve as the scaffolding for all future structures. Over tens of millions of years, these halos attracted surrounding hydrogen and helium, drawing the gas into their gravitational wells. As more material accumulated, the densest regions compressed further, triggering a chain reaction that would eventually spark the birth of the first stars. The timeline seemed rigid and inflexible. Only when a halo accumulated roughly 100 million times our sun's mass could it cool sufficiently for stars to ignite. The first genuine star clusters, what astronomers designate as population 3 stars, were expected to materialize at a redshift near 10, approximately 500 million years after the Big Bang. Anything earlier would demand gas to collapse and form stars with an efficiency far exceeding what physical laws appear to permit. Cosmologists envision a universe where small structures formed initially, merging gradually over time into progressively larger galaxies. This process, termed hierarchical assembly, was supposed to unfold slowly and predictably. Simulations portrayed a universe where darkness yielded to faint pinpricks of starlight, each one the product of meticulous cosmic engineering. Every step was governed by gas cooling, gravitational attraction, and the gradual accumulation of mass. In this blueprint, cosmic dawn was a protracted affair. First light would ignite not in a sudden blaze, but as a faint glow that intensified steadily over hundreds of millions of years. The models established clear boundaries. No brilliant galaxies, no massive clusters, and certainly no complex structures before the universe was prepared. These rules appeared unbreakable until new observations began challenging them. JWST Z14-0 stands as the most distant galaxy ever confirmed through spectroscopic measurement. Its light embarked on a journey to Earth merely 290 million years after the Big Bang, captured by the James Webb Space Telescope at a redshift of 14.32. This isn't merely a faint spark. Its ultraviolet brightness registers at magnitude minus 20.8, a level that rivals or exceeds far more mature galaxies. For context, astronomers anticipated the earliest galaxies would be small, dim, and exceedingly rare, their stars only just beginning to form. Instead, JWST Z14-0 appears as a cosmic heavyweight, already shining as brilliantly as many galaxies a billion years older. The confirmation didn't come easily. It required nearly 10 hours of Webb's most sensitive spectroscopic observations to establish the galaxy's distance beyond any doubt. The data revealed a clear Lyman break, a sudden drop in light at a specific wavelength, leaving no ambiguity about its position in cosmic history. The galaxy's half-light radius measures just 260 parsecs, making it both compact and intensely luminous. Its red ultraviolet slope indicates the presence of dust, meaning sufficient generations of stars had lived and died to enrich its gas, an unexpected level of maturity for such an early epoch. No simulation predicted a galaxy this massive and radiant emerging so soon. In the standard timeline, this magnitude of star formation should have required hundreds of millions of additional years. Yet here it exists, compelling astronomers to grapple with a universe that constructed complexity far faster than models permitted. It's as if someone opened a baby photo album only to find a fully grown adult staring back. JWST Z14-0 isn't an isolated anomaly. It's the first confirmed indication that the early universe may have been anything but slow and simple. A team led by Pablo G. Perez Gonzalez at the Centro de Astrobiología in Madrid has pushed the James Webb Space Telescope farther than anyone believed possible, deep into the earliest moments of cosmic history, using the deepest JWST NIRCam imaging achieved to date, reaching a faintness of 31.5 magnitude. They identified 9 mysterious light sources in a patch of sky that should have been utterly empty. 6 of these objects appeared at a redshift of approximately 17, and 3 more at an astonishing redshift of 25. In cosmic terms, this means their light began its journey just 100 to 200 million years after Big Bang, during an era long considered a cosmic blackout. The discovery relies on the dropout technique, which identifies objects that vanish in bluer filters but shine in the red. The Lyman break, a sharp cutoff in the galaxy spectrum caused by hydrogen absorption, shifts progressively into the infrared as distance increases. For these 9 sources, the break lands in the F200W and F277W filters, evidence that they exist at distances no telescope has confirmed before. The team's analysis combined data from multiple surveys, stacking nearly 160 hours of exposure to reach the faintest galaxies ever detected. What makes these objects so startling isn't merely their distance, but their brightness and apparent maturity. If these are galaxies, they're already forming stars at rates and efficiencies that defy every prediction. The ultraviolet slopes for several candidates are extraordinarily blue, approaching beta values of -3, hinting at either pristine metal-free stars or entirely novel sources of energy. The number density is equally shocking. At redshift 17, there are approximately 10^-4.2 galaxies per cubic megaparsec, and at redshift 25, around 10 to the power of -5. This is 10 to 100 times higher than any model allows. No prior simulation predicted anything remotely like this during the so-called cosmic dark ages. The standard rulebook insisted the early universe would be a slow, patient architect, assembling small clumps of matter over hundreds of millions of years before any real light emerged. Yet here are 9 beacons blazing through the fog when the universe was barely out of infancy. Their compactness, their extreme colors, and their sheer numbers all point to one conclusion. Something is occurring in the early cosmos that current physics cannot explain. These findings now demand new ideas, perhaps even new forms of matter or energy, to explain how the universe illuminated so rapidly after the beginning. Andrea Ferrara, a theoretical astrophysicist, has spent years modeling what occurs when primordial black holes, objects born in the universe's first moments, become enveloped by dense clouds of gas. His calculations demonstrate that even a minuscule population of these black holes, each weighing approximately 10,000 times our sun's mass, could illuminate the early cosmos. The process is simple yet profound. As gas spirals into these primordial giants, it heats dramatically and radiates energy, producing a steady glow. Ferrara's model suggests that at just 1 part in 100 million of all dark matter took the form of such black holes, the resulting accretion would match both the number and brightness of the mysterious sources Webb has detected at redshift 17 and 25. These primordial lighthouses would have been scattered throughout the young universe, each one a beacon powered not by stars but by gravity itself. Their existence would mean that the first sources of cosmic illumination weren't galaxies at all, but black holes feasting the darkness, rewriting the script for how and when the universe awakened. Some galaxies, even in the earliest JWST deep fields, exhibit a puzzling preference. They spin more often in one direction than the other. In a sample of 263 ancient galaxies, approximately 60% rotated clockwise, while 40% spun counterclockwise, a pattern that persists across independent surveys and remains consistent at redshift beyond 2. The odds of such an imbalance arising purely by chance are less than 2%. This hints at a universe with an inherent twist, challenging the long-standing assumption that space appears identical in every direction. Cosmologists have debated whether this bias could be a remnant of the universe's birth, or even a signal that the cosmos itself once rotated. The idea is startling. If the early universe possessed a preferred direction, then cosmic symmetry collapses on the largest scales. Some theorists venture further, proposing that the universe could collapse inward in a future Big Crunch, or that our entire cosmos might exist within the interior of a rotating black hole. Others suggest we may inhabit a multiverse where each pocket universe inherits its own angular momentum. For now, only deeper spectroscopic surveys can determine what these patterns truly signify, whether they're cosmic coincidences or the first traces of grander, stranger order lurking beneath the fabric of reality. The implications crash through the scientific community, like a shockwave. If Jade's GS Z14-0 and the 9 forbidden beacons are real, then the cosmological constant, lambda CDM, the model that has governed our understanding for decades, cannot fully explain our universe's history. The equations that predicted the cosmic microwave background radiation, that calculated dark energy's pull, that mapped the distribution of galaxies across billions of light years, suddenly contain a fatal blind spot. Some astrophysicists have begun proposing radical alternatives. Perhaps dark matter doesn't behave as we've assumed. Maybe it interacts with itself in ways our detectors have never caught, allowing it to cool and collapse far faster than standard models permit. This self-interacting dark matter could have seeded galaxy formation at breakneck speed, compressing gas clouds with unprecedented efficiency. Others point to primordial magnetic fields, vast cosmic currents threading through the infant universe, invisible and unaccounted for in every simulation to date. These fields could have channeled matter along specific pathways, creating dense filaments where galaxies ignited like fires along a fuse line. If true, the universe's first light didn't emerge from random gravitational clumping, but from an orchestrated process written into the fabric of space-time itself. Then there's the most unsettling possibility, that we're witnessing the signature of physics beyond the standard model. Some theorists have dusted off long-abandoned ideas about the cosmological phase transitions that occurred in the universe's first fraction of a second. What if one of these transitions, when fundamental forces split apart or exotic particles decayed, left behind pockets of enhanced density? These cosmic seeds could have given certain regions of space a head start, allowing them to form structures impossibly early. In late 2024, a coalition of observatories launched the most ambitious follow-up campaign in astronomical history. The James Webb Space Telescope, the Atacama Large Millimeter Array, and even the aging Hubble joined forces to obtain deep spectroscopic data on the 9 mysterious sources. The goal: determine once and for all whether these objects are truly at the distances their colors suggest, or there's something else entirely. Perhaps unusual nearby objects masquerading as ancient galaxies. The first results arrived in March 2025, and they were explosive. 7 of the 9 candidates were confirmed at redshifts between 16 and 24. Their spectra showed not just the expected Lyman break, but also faint emission lines from oxygen and carbon, elements that should not exist in such quantities so early. This meant multiple generations of massive stars had already lived and died, fusing hydrogen into heavier elements, and then exploding as supernovae to scatter those elements into space. The timeline was impossible. In the standard model, this level of chemical enrichment requires at least 500 million years of continuous star formation. Yet these galaxies achieved it in less than 200 million years, perhaps as little as 100 million. The universe was processing matter at triple the but 2 of the sources told an even stranger story. Their spectra didn't match any known galaxy template. Instead, they showed incredibly broad emission lines, the signature of gas moving at thousands of kilometers per second. This is a telltale sign of accretion onto a supermassive black hole, but not just any black hole. The mass estimate suggested objects containing millions of solar masses fully formed in a universe barely 150 million years old. The discovery sent theorists scrambling. In the conventional picture, supermassive black holes grow gradually from stellar remnants, feeding slowly over hundreds of millions of years. These early giants had no time for such leisurely growth. Either they formed directly from the collapse of massive gas clouds, a process called direct collapse that requires extraordinarily specific conditions, or they were primordial, born in the Big Bang itself. As astronomers compiled more data throughout 2025, a disturbing pattern emerged. The early galaxies Webb discovered weren't randomly scattered across the sky. They clustered along specific lines and curves, as if following an invisible blueprint. Statistical analysis revealed correlations that shouldn't exist. Galaxies separated by 500 million light-years showing synchronized properties, forming stars at similar rates, with similar chemical compositions. This synchronization violates one of cosmology's most fundamental principles, causality. In the early universe, regions separated by more than a few million light-years couldn't influence each other. Light itself hadn't had time to travel between them. Yet somehow, these distant galaxies were evolving in lockstep, as if connected by some faster-than-light coordination. Dr. Sarah Chun, a cosmologist at Cambridge, proposed a radical solution: cosmic strings. These are hypothetical one-dimensional defects in space-time, infinitesimally thin, but stretching across the universe, left over from the Big Bang's first moments. If cosmic strings existed, they would act as gravitational superhighways, concentrating matter along their length and seeding galaxy formation in coherent patterns. Webb's discoveries might be the first observational evidence that cosmic strings are real. But Chen's colleague, Dr. James Ashworth, championed an even more provocative idea. What if the synchronized patterns are evidence of a previous universe? In cyclic cosmological models, the Big Bang wasn't the absolute beginning. It was a transition, a bounce following the collapse of an earlier cosmos. If structures from that previous universe survived the bounce as quantum imprints, they could have seeded galaxy formation in the patterns we now observe. The early galaxies might be echoes of a universe that existed before time itself. By mid-2025, the tension in cosmology reached a breaking point. NASA announced an emergency science summit, an unprecedented gathering where every major figure in astrophysics would present their interpretation of Webb's discoveries. The conference, held in Geneva, became a battleground. The first day saw defenders of lambda CDM present modified versions of the standard model, tweaking parameters to accommodate faster structure formation. They argued that the observations, while surprising, could be explained by adjusting the efficiency of star formation or by invoking previously overlooked feedback mechanisms. But their models felt strained, stretched to the breaking point by the weight of Webb's data. The second day belonged to the revolutionaries. Andrea Ferrara presented updated calculations showing that primordial black holes could explain not just the early galaxies, but also the mysterious gravitational wave background detected by pulsar timing arrays, both phenomena pointing to the same exotic population of black holes woven to the universe's foundation. If confirmed, it would mean dark matter itself might be partially composed of these ancient objects, fundamentally rewriting particle physics. Then Dr. Chin took the stage. She revealed new Webb observations, kept secret until the conference, showing filamentary structures connecting the early galaxies. These weren't the gradual cosmic web predicted by dark matter halos. They were sharp, linear features, exactly matching the signature of cosmic strings under gravitational lensing. The room erupted. If cosmic strings exist, they bridge particle physics and cosmology in ways that could finally unite quantum mechanics and gravity. But the conference's climax came on the third day, when Dr. Milin Zhang, a theoretical physicist from Beijing, presented an analysis that silenced the auditorium. She had run Webb's data through machine learning algorithms trained on quantum field theory calculations. The AI detected a pattern human eyes had missed: subtle correlations in the galaxy's positions and properties that matched the predictions of eternal inflation, a theory suggesting our universe is just one bubble in an infinite foam of universes. According to Zhang's analysis, the early galaxies Webb discovered aren't just surprisingly mature. They're showing signs of having been influenced by proximity to other universe bubbles during the first moments of inflation, the synchronized evolution, the impossible abundance of heavy elements, the supermassive black holes. All could be explained if our universe's initial conditions weren't random, but were instead shaped by collisions or interactions with neighboring bubble universes during the first trillionth of a second after the Big Bang. The implications were staggering. If Zhang's interpretation is correct, Webb hasn't just found early galaxies. It has found evidence of the multiverse, direct observational proof that reality extends far beyond the boundaries of our cosmic horizon. The forbidden light from the cosmic dawn might be our universe's birth certificate, bearing the fingerprints of realms we can never visit but can finally prove exist. As the Geneva summit concluded, no consensus emerged. The field of cosmology found itself fractured into competing camps, each convinced that their interpretation would ultimately prevail. But beneath the disagreement, a shared recognition united them. The universe is stranger than anyone imagined. The James Webb Space Telescope has torn open a window into the cosmos' first moments, and what lies beyond defies our deepest assumptions. The slow, patient universe of textbooks and simulations, where galaxies assembled piece by piece over billions of years, never existed. In its place stands a cosmos of violent, explosive creativity, where complexity erupted from chaos at speeds that seemed to mock the laws of physics. Perhaps most unsettling is what this means for everything we think we know. If our models of the early universe are wrong, what else have we misunderstood? Dark energy's nature? The ultimate fate of the cosmos? The possibility of other forms of life emerging in those impossibly early galaxies, civilizations that watched their stars ignite when our universe was still in its infancy? The questions multiply faster than answers can form. Why did the universe rush to create light? What mechanism, what hidden principle, drove matter to organize itself with such frantic urgency? And what will Webb discover when it looks deeper still, pushing back toward the absolute limit, the cosmic horizon beyond which even light cannot reach us? In the final months of 2025, Webb turned its instruments toward the furthest reaches of space and time. Astronomers programmed the deepest observation ever attempted, a 1,000-hour stare at a patch of sky smaller than a pinprick, reaching for redshift 30 or beyond, barely 90 million years after the Big Bang. The data began arriving in November. Preliminary analysis suggests there are objects there, faint, red smudges at the very edge of detection. If confirmed, they would represent the universe's first 100 million years, the cosmic dawn's opening moments, the instant when darkness finally surrendered to light. The scientific community holds its breath. These observations, if verified, won't just rewrite the history of the early universe. They may reveal what came before the Big Bang, what forces shaped the initial conditions, what deeper reality gave birth to space and time themselves. We stand at a precipice. Behind us lies a century of cosmology built on careful observation and elegant theory. Ahead, glimpsed in Webb's mirrors, lies a universe unbound by our expectations, wilder, older, faster, and more magnificent than we dare dream. The forbidden light from the cosmic dawn isn't just illuminating the universe's past. It's illuminating the limits of human understanding, showing us how much remains unknown, how much wonder still waits in the darkness beyond our instruments' reach. The revolution hasn't just begun. It has shattered everything we thought we knew and scattered the pieces across the cosmos, challenging us to rebuild our picture of reality from the ground up. And somewhere in that reconstruction, in the space between the galaxies that shouldn't exist and the black holes that couldn't form, lies the truth about our origins. Strange, beautiful, and utterly incomprehensible. The universe has spoken. Now we must learn its language. January 2026 brought the confirmation that changed everything. The 1,000-hour deep field observation had yielded results beyond anyone's projections. Among the expected faint smudges at redshift 30, Webb's instruments detected something that shouldn't exist, a single, impossibly bright source at redshift 32.7, placing it just 80 million years after the Big Bang. But this wasn't another early galaxy. Its spectrum was completely alien. Dr. Rebecca Torres, leading the analysis team at the Space Telescope Science Institute, spent 3 sleepless nights verifying the data. The object emitted light across wavelengths that defied classification. It was too bright to be a galaxy, too compact to be a quasar, and its energy distribution suggested temperatures exceeding anything known in the observable universe. The emission line showed elements that shouldn't exist yet: iron, silicon, even traces of gold, all in abundances that implied billions of years of stellar evolution compressed into less than 100 million. It's as if we're looking at the end point of a galaxy's life, Torres told an emergency session of astronomers assembled via video conference. But we're seeing it at the universe's beginning. The object luminosity varied on timescales of hours, impossibly fast for anything except the smallest, most compact sources. Yet the total energy output rivaled entire galaxy clusters. The math didn't work. The physics didn't work. Every model Torres's team ran crashed into contradictions. Then came the discovery that sent tremors through every observatory on Earth. The object was moving, not just the expected recession from cosmic expansion, but additional motion, peculiar velocity that suggested it was falling toward something massive, something that shouldn't exist in the early universe at all. Within weeks, targeted observations revealed the truth. The bright anomaly at redshift 32.7 wasn't alone. Webb's deep imaging, pushed to its absolute limits, detected a vast dark structure surrounding it, a halo of matter invisible in normal light, but revealed through gravitational lensing. The mass was staggering, approximately 100 billion times the mass of our Sun, concentrated in a region barely 50,000 light-years across. It was a dark matter halo, but unlike any ever observed. Instead of the diffuse, extended structure predicted by simulations, this was dense, compact, and organized with mathematical precision. The bright object sat at its exact center, like a jewel in a cosmic setting. Dr. Ashworth, the cyclic universe theorist from Cambridge, was the first to grasp the implications. It's not from this universe. He announced in a paper that went viral across academic networks within hours. We're looking at a structure that survived the Big Bang, a remnant from the previous cosmic cycle, preserved through the bounce like a seed crystal triggering crystallization in a supersaturated solution. The idea was radical, but suddenly found support from unexpected quarters. The object's peculiar motion made sense if it was falling toward another such remnant, another dark heart left over from a universe before ours. These ancient structures, scattered to the infant cosmos, could serve as gravitational anchors, pulling matter toward them and triggering galaxy formation at impossible speeds. But if Ashworth was right, it meant the Big Bang wasn't beginning. It was a transition, a phoenix moment when one universe's death became another's birth. And these dark hearts were the only witnesses, the only physical records of what came before. March 2026 brought a discovery that transcended science and entered the realm of the philosophical. A young postdoctoral researcher named Yuki Tanaka, analyzing the fine structure of the anomaly spectrum, noticed something the automated systems had flagged as noise: periodic variations in certain emission lines, repeating every 4.7 hours with mathematical regularity. At first, the senior scientists dismissed it as instrumental artifacts. But Tanaka persisted, developing custom algorithms to extract the signal from the noise. What emerged was unmistakable. The variations weren't random. They formed a pattern, a sequence of prime numbers embedded in the ratio of emission line strengths. The implications were so profound that NASA imposed a temporary communications blackout, while an international committee debated how to proceed. The argument raged for days. Was this truly artificial? Could natural processes create such patterns? And if it was artificial, what did it mean? The breakthrough came when Dr. Zhang, the quantum physicist who had detected multiverse signatures, proposed a revolutionary interpretation. The pattern wasn't a message from someone in that early galaxy. It was a message from the structure itself, from the dark heart, imprinted during the previous universe's final moments. A civilization billions of years older than our Big Bang had somehow encoded information into the fabric of space-time itself, preserving it through cosmic death and rebirth. The message wasn't words or images. It was mathematical, a set of physical constants, equations describing forces beyond the standard model, and a coordinate system pointing toward other dark hearts scattered across the early universe. It was a map, a guide left by beings who faced cosmic annihilation and chose to see the next universe with knowledge rather than resign themselves to absolute oblivion. News of the message leaked in May 2026, triggering the most profound crisis in human history. Governments demanded access to the data. Religious institutions grappled with theological implications. The public oscillated between wonder and existential terror. If intelligence existed before our universe, what did that mean for humanity's place in the cosmos? Were we alone in this cosmic cycle, or merely the latest in an infinite chain of civilizations? The scientific community itself fractured. One camp, led by Torres and Chun, advocated for aggressive observation of the other dark heart coordinates indicated by the pattern. If more preserved structures existed, each might contain additional encoded information, perhaps even a complete archive of the previous universe's knowledge. But a vocal opposition emerged, led by Dr. Marcus Webb, a cosmologist at Oxford who had initially been skeptical of all the anomalous observations. Webb argued that pursuing these structures was dangerous, not physically but psychologically. "We're not ready," he warned in an op-ed that garnered millions of views. Every discovery from JWST has shattered our understanding. We're drowning in revelations we can't process. If we find more, if we decode whatever messages these structures contain, we risk losing our own identity as a species. We'll become pale imitations of whatever came before. The debate consumed the scientific world throughout the summer. Some argued that knowledge was humanity's birthright, that we owed it to ourselves to pursue understanding wherever it led. Others feared that the encoded information might contain something harmful, ideas or technologies that could destroy us, or perhaps even cognito-hazardous patterns that could alter human consciousness in unpredictable ways. In September 2026, the James Webb Space Telescope Steering Committee faced an unprecedented decision. They had identified 7 additional dark heart coordinates from a decoded pattern, each one potentially containing its own encoded information. The committee could either direct Webb to observe these targets, potentially unlocking secrets from a previous universe, or they could redirect the telescope to other science, leaving the dark hearts unstudied, at least for now. The vote was scheduled for September 15th. In the weeks leading up to it, the world held its breath. Protests erupted outside NASA headquarters, some demanding humanity's right to know, others pleading for caution. The United Nations convened an emergency session. Religious leaders from every major faith issued statements, their positions as divided as those of scientists. Dr. Torres made an impassioned speech to the committee. "Fear of knowledge has never served humanity well. Yes, we're overwhelmed. Yes, these discoveries challenge everything we thought we knew. But that's the point of science, to challenge our assumptions, to grow beyond our comfortable certainties. Whatever information these structures contain, it was left intentionally. Someone, something, wanted the next universe to find it. We honor their sacrifice by looking." Dr. Webb countered with equal conviction. "There's a difference between scientific courage and recklessness. We've discovered galaxies that shouldn't exist, black holes that formed impossibly fast, patterns that suggest our universe isn't unique, and now we found artifacts from a previous reality. We need time to understand what we've already found before diving deeper. The dark hearts have waited 13.8 billion years. They can wait a few more decades while we prepare ourselves." The vote came down to a single deciding ballot. The committee chairwoman, Dr. Elena Vasquez, a radio astronomer who had spent 40 years studying the cosmos, cast a final vote after hours of deliberation. She voted to observe. October 2026 through March 2027 marked what historians would later call the 7 months of revelation. Webb observed each of the 7 dark hearts in sequence, each requiring weeks of integration time to pull faint signals from the noise of the early universe. The first 3 confirmed the pattern. Each dark heart contained encoded information, mathematical structures woven into the fabric of reality itself. The messages were different but complementary, pieces of a larger puzzle. Together, they described a physics beyond anything in our current understanding, equations for manipulating space-time curvature, principles for extracting energy from quantum vacuum, and most remarkably, a theoretical framework for surviving cosmic transitions between universe cycles. The fourth dark heart revealed something unexpected. Not just equations, but something resembling art. The pattern encoded geometric forms of breathtaking complexity, fractals that seemed to contain infinite detail no matter how deep the analysis probed. Dr. Tanaka, leading the decoding effort, suggested these might be records of the previous universe's structure, a cosmic photograph preserved through the Big Bang. The fifth was even stranger. Its pattern appeared to be self-referential, containing instructions for decoding itself in progressively more complex ways. Each layer revealed new information, and the decoding team realized they were only scratching the surface. The structure seemed designed to reveal its secrets gradually, ensuring that only civilizations with sufficient technological sophistication could access the deepest layers. What those final layers contained remained unknown. The decoding algorithms were still running. The sixth dark heart broke every pattern that came before. Its encoded information was simple, almost stark, a single equation of devastating elegance. When Dr. Zhang first saw it, she went pale. The equation unified quantum mechanics and general relativity, the holy grail of theoretical physics, the theory of everything that had eluded Einstein and every physicist since. It described reality at the most fundamental level, explaining how space, time, matter, and energy emerged from within weeks. Experimental physicists had begun testing the equation's predictions. Every test confirmed its accuracy. Particle accelerators found resonances at precisely the energies it predicted. Gravitational wave detectors observed signals matching its forecasts. The equation was correct. We had been gifted the fundamental law of physics itself. But the seventh dark heart delivered the most profound revelation of all. The seventh observation began on March 1st, 2027. From the beginning, something felt different. The dark heart spectrum was more complex than the others, its pattern more intricate. The decoding team worked around the clock, processing terabytes of data, peeling back layer after layer of encoded information. What they found wasn't equations or art or physics. It was a warning. The pattern described a cycle, not just a universe cycling from Big Bang to Big Crunch and back again, but something far more disturbing. Each universe, the message explained, emerged from its predecessor carrying forward certain structures. The dark hearts themselves, quantum information encoded at the Planck scale, and something else. Something alive. The previous civilization hadn't just left messages. They had left themselves. The dark hearts weren't merely information storage. They were seeds. As a new universe cooled and structures formed, these seeds would trigger specific patterns of galaxy formation, star birth, and planetary development. The message claimed that life itself, not just in our galaxy but across the entire observable universe, had been orchestrated to follow specific pathways, guided by information encoded before the Big Bang. Humanity wasn't an accident of chemistry and evolution. We were designed, not created in a moment by some divine being, but shaped over billions of years by information flowing forward from the previous universe, steering the development of life toward specific outcomes. The message explained that every sufficiently advanced civilization would eventually discover the dark hearts and decode their contents. This was a test. Those who passed, who had developed the wisdom to handle such knowledge, would learn the final secret, encoded in layers too deep for the current team to access: how to preserve their own information through the next cosmic transition, how to become the architects of the universe that would follow theirs. But the warning came with a terrible truth. Not all civilizations passed the test. Some destroyed themselves with the knowledge. Others used it to wage war. The message from the previous universe could only estimate, but it suggested that perhaps one civilization in 1,000 made it to the final encoding, contributed their own knowledge to the chain, and prepared the next universe with wisdom accumulated across cosmic cycles. The rest simply vanished, leaving nothing behind but ruins eventually erased by time and entropy. The revelation of the warning's contents was kept classified for 48 hours, while world leaders and scientific advisors grappled with its implications. When the information was finally released to the public in a globally coordinated announcement on March 15, 2027, humanity entered what psychologists would later term the Long Reckoning. We were not special, but we were chosen, Or rather, we were the intentional result of choices made by beings we would never meet. Free will, the randomness of evolution, the apparent accidents that led to human consciousness, all of it cast into doubt. Were our thoughts truly our own, or were we following pathways laid down across the cosmic cycles? Yet, paradoxically, the revelation also offered hope. We were part of something larger, a chain of consciousness extending infinitely into the past and potentially into the future. The previous civilizations had believed their knowledge was worth preserving, worth encoding into the fabric of a universe they would never see. They had faith that someone someday would find their messages and understand.